coming at this very much from a design perspective. It's great to see that previous presentation and the advances in the technology. But as a designer, I'm interested in what we can do with the technology itself. I'm less interested, I suppose, with mimicking other manufacturing techniques and really exploring what we can do with AM and 3D printing. So I'm currently Associate Dean for Practice at NTU. Practice is our kind of umbrella term for knowledge exchange, enterprise, and practice-based activities. I'm also Professor of Design there. Before that, I had a bit of a hiatus from additive manufacturing when I was at Montfort University. I was head of design, but I was also director of the design unit, which was a design consultancy. And we were very much working with SMEs and companies on new product development and exploring, the design process. And that did include a little bit of using 3D printing. But the bulk of my work in AM was done when I was at Loughborough University. I spent the best part of 10 years there, working with people like Patrick, Abby, Richard Bibb, where we all got together, and I ended up being the head of the Digital Fabrication Research Group. And my interest in 3D printing and AM is very much, the design side of it. I've been working in this, I was actually astonished that it was like 2003, so I've now been working in this area for like 20 years. And it is about the applications and implications of design for 3D printing. I've done a lot of work in 3D printed fashion and footwear, but of course I operate in sort of the design thinking, design practice sort of realm. So design opportunities for AM. I'm talking to a very enlightened group, I imagine, and we know this is incredibly disruptive technology, and we could talk about material usage, we could talk about localized manufacturing. But again, as I said earlier, I'm interested in what we can do with this technology in itself, not mimicking other sort of mainstream conventional manufacturing techniques. And for me, this is about unlimited geometry freedom. And we often talk about with AM, we're sort of removing all the design for manufacturing constraints, and that's really appealing for designers because we design for manufacture, making considerations for the manufacturing process, really detracts from our design intent. But we have to be mindful that yes, we're sort of removing conventional manufacturing considerations, but we're not removing all the manufacturing considerations. But for designers, the fact that we're not concerned by tooling, 3D CAD becomes our tool, which is fantastic. We haven't got to worry about things like part extraction from a tool, draft angles, split lines, and suddenly it sort of lifts the lid on things like re-entrant and complex geometry. And I've got an image here, which obviously will be very familiar to Candy. The kind of things that we can do with 3D printing are astonishing in comparison to sort of normal conventional manufacturing techniques. So obviously this is a 3D printed wedding bouquet, manufactured as a single unit, astonishing geometry freedom. And I have this very sort of whimsical equation, which makes engineers wince. When I say that design complexity is really, when we're talking about AM and 3D printing, really equals the imagination of the designer times their 3D modeling capabilities. So anything you can realize and imagine, 3D printing can generate. Oh, we're still sharing? Hello?
Yeah, you're still sharing. Have you moved on to the next slide yet or not?
No, I have now.
No, yeah, no, you're good.
Okay, so some of the opportunities, AM presents include things like design optimization. Now, topological optimization, it's been around for a good long while, but it's now becoming really, really accessible to sort of mid-tier 3D CAD platforms. Things like, it's embedded with SolidWorks, it's embedded with Autodesk. And this is about taking your geometry and its existing state, providing a loads of constraints, so fixture points, and then using an FEA type process to work out all the stresses and strains on your object, and then removing material where it's not required. And this truly gives you an optimal sort of optimized structure. And we're seeing this done, in conventional parts for fixtures and fittings, but we're also seeing this more in the design sphere. So we see an example here. This is the Generico chair by Marco Helmeling. And this is really using 3D printing to its full potential. So it does create a particular aesthetic, but this is something that can be created using more conventional manufacturing techniques. And then moving on from that, we can sort of explore the sort of the generative design aspects. Now these objects aren't designed to be optimized in terms of some kind of performance characteristic or weight distribution or material usage. This is about just exploring organic and sort of lattice structures. So, and this has become much more accessible through things like Grasshopper and 3ds Max. So I've got some examples that I've done quite a while ago now. So the street furniture, again, this isn't an optimized structure, but it's using that particular sort of visual language and aesthetic that can only be realized through sort of 3D printing and additive techniques. And of course, we can explore, really, really complex geometries and organic sort of cellular structures. And you can see that on the right through, this is a bit of 3D printed art sculpture. But obviously this could be extended to, conventional design of products and fixtures and fittings, and be incorporated into that sort of general visual language. Moving on from there, we have design opportunities in personalization and customization, additive manufacturing, because we're not constrained by tooling, and obviously 3D CAD is our tool. It allows us to explore things like the economic manufacture of a single unit, or N equals 1. And that allows us to do things like complete bespoke designs, or engage in things like co-design and co-creation. So we have the example here from Lionel Dean, and this is obviously going back a few years now. And it looks like a pretty standard 3D printed lamp, because obviously the market has now been inundated with this stuff. But this was actually based on co-creation. So there was an algorithm deciding this geometry. And through an animation, this would play and evolve and develop over time. And as a consumer, you could co-create. You could stop the animation at any point and then have that printed out. And that is a capability that's only been realized through additive techniques. But then, of course, we can also engage in things like personalization for the individual. So we can engage in body fitting, and I know that there's going to be some medical applications presented later on. Things like implants, where it is entirely bespoke to a single user. But here we have an example from Bespoke Innovations and some of the Scott Summit work. Summit work, where he was looking at prosthesis. So not only was he using personalization and the capabilities of 3D printing to recreate the fairing here, but also engaging in co-creation and co-design to actually do the more sort of functional aspects of the prosthesis, and then obviously match that to the user's requirement, their particular aesthetic, their lifestyle choices. And again, something that can only be realized through 3D printing. I think we're all quite familiar with the opportunities in terms of part consolidation. So we have quite a nice example here from Proto Labs. So this is the design journey of a distribution manifold. So it would have been a pretty traditional part using traditional conventional manufacturing techniques, injection molding, machining, etc., and a whole host of assembly. But through 3D printing, obviously, we can go through an iterative design process here to not only to reduce the parts, but then optimize those parts. So we go through a stage of initially 11 parts, we can reduce that to 7. And again, that can be further sort of designed and refined to become a single part. And then you can engage in things like, obviously, design optimization, topological optimization, to reduce the weight and increase the performance. But it gives us the opportunity to think about how we can use the design potential to integrate things like fasteners, fixtures. We talked a lot about live hinges, but springs. There are real opportunities here for improving the design of just conventional everyday stuff. And then we have a personal favorite of mine. This is where I spent a lot of my research time. It's thinking and using the technology and its capabilities to create things like multiple free moving assemblies that are manufactured in a single process and require no sort of assembly afterwards. Now, everyone's probably seen, the nice desk toys of integrated gears and switches and movements and levers. But what we were doing was looking at how we could use this technology to generate some chainmail type textile structures. Now, originally, back in 2003, we were using laser sintering, and we were constrained by the resolution of the time. But now the technology has moved on so much, and thank you to Mark in the previous presentation to demonstrate some of the advances in the technology. But the resolution is getting better and better. The materials are getting better and better. So we can explore things like coloration. We can explore finer and finer textiles. We're exploring footwear, how we can print this out. And I know there's been a lot of work done on 3D printing of the midsole, but the actual textile upper and the chainmail type way. But also integrating and reducing sort of the process steps in assembly. It's like we can now print out a zip with a textile in a single go, and that's going to be fully functional. Or we could grade functionality through things like 3D printed clothing. So this was an early example of some of the research that we did looking at PPE and stab protection, how we have different types of textiles, free moving assemblies at different parts and locations of the body to provide the protection needed. And then we have also the opportunity to work at different scales. Now, we're all used to printing out stuff that's at the macro sort of scale that we're used to handling in our hands. But that sort of design complexity translates through to the micro scale. And we are seeing, the resolution capability of the 3D printing improving all the time, especially in some of the jetting and the LDP technologies. So it allows us to explore sort of a micro world that we don't previously have access to. Now, these examples are from Nanoscribe, and you've got some scales there for reference, like obviously this is 1 micrometer, but this is less than the width of a human hair, and you're getting that ability to do complex geometry at a really, really small scale. And that allows us to explore some really interesting stuff in terms of design, in terms of surface textures. Could they be functional? Are we not just having the surface of an object? We can actually have that as a functional part of our design process. And that's really interesting. And then obviously the previous presentation also touched on lots of different materials, and they're developing at a phenomenal rate. The portfolio of materials now available in 3D printing is astonishing. And the design opportunities for that are really, really interesting. New composite materials that could be applied to different environments or different applications. But we're also seeing the opportunity to do multiple materials in a single build, and how we grade the functionality between something that's very rigid to something that's very soft and everything in between. And some of the early work by Iris van Herpen in sort of the haute couture fashion area was looking at how we mix materials to create something really, really interesting, something that would have motion and flow and feel. And also, I was astonished to see the in-process coloration actually, and the ability to print out the beer bottle on the previous presentation. But color to design is non-trivial. We are very concerned with what we call CMF, so color, material, finish of our objects, and that ability to color different parts of the object, provide highlights. That really speaks to us in terms of a design opportunity. So obviously, I painted a picture there that we've got this unlimited design freedom, and we're not constrained by any sort of design for manufacturing considerations. And I don't want to leave you with that because that is not entirely true. When we're talking about using additive techniques, we are, yes, getting rid of all the conventional sort of considerations for manufacture, but we are introducing a whole new set that are both process specific, and we're seeing the range of processes explode. But also geometry specific as well. So you do have to engage in a slightly different sort of detailed design process. And I'm not going to go through all of this in detail. But within the 3D modeling, we have to ensure that our 3D models are absolutely watertight and accurate. You've got to think about whether we're using the technology to mimic something else, or it is about utilizing this technology as additive manufacturing and therefore the end-use process. But there's a whole load of sort of pre-processing in terms of the data and setting up the machine, and this is kind of the underbelly of additive manufacturing that not always gets discussed. And then there's always going to be some kind of post-processing. That's getting better and better and better at getting the part out, cleaning it up, looking at surface finish. Coloration is obviously getting better and better, but depending on the type of material you use, there might be some additional work there. So in terms of design for additive manufacturing considerations, yes, we've demonstrated that you can work at the micro scale, but there are generally minimum feature sizes that you want to print within a particular material. If we go smaller than that, it's not going to have the mechanical properties we need to provide the function within the design that we're trying to deliver. And you've also got to think about part separation and how we design for tighter tolerances. If parts are obviously touching within our 3D CAD environment, they're going to be a solid fused part when they come out. But you can use the design opportunities within additive manufacturing to kind of cheat the process. So, you know, if we had to design, you know, a collar on a shaft or a bearing on a shaft for a particular design, it's how you use the design freedom to reduce those contact points, reduce that separation, and then mechanically free them later on. So it's quite interesting. It's about being clever with your design work. And of course, you know, hollowing out parts and shells, that's become very much automated now within the CAD system itself. But also, you know, depending on the process we're using, we're going to have support structures. Some of those are going to be soluble, some of those are not, depending on the type of material you use. And it's how you place them. Do you let the software automatically do it, or do you design your geometry to limit the amount of support structures required? And then, especially with the powder-based systems, we often talk about, you know, the ability to do conformal channels. And some of the examples I've shown where we've got like really complicated geometries, how do you get that powder out? You know, sometimes that is an absolute nightmare. But again, it's about using the design freedom of the process to aid you with that problem. So some of the work that we did earlier on in laser sintering, you know, if we wanted to do a conformal channel, obviously this would be absolutely full of powder, and we'd have a really tough time trying to get this out of the actual part itself. But you could just print a chain. You could, within your 3D CAD, you could actually model a chain in that conformal channel as a sacrificial geometry, and then use that when you're doing the post-processing cleanup of your part. Just pull on either end, loosen up that powder, and then just drag it all out. Yeah, so it's about understanding what the technology can do, but then using its full potential to realize the geometry that you want. Okay, so design opportunities, you know, unrivaled disruptive technology in terms of design freedom. You know, the ability to create complex geometry it far outweighs anything else that's currently available. You know, the opportunity to optimize our design, you know, are becoming increasingly easy for designers, because all of those techniques and all those strategies are now being built in and really made easy to use in terms of a usability and a workflow. That ability to personalize and customize your design work and engage in things like co-creation, that's really interesting from a design point of view. You know, we're not constrained by making large batches of stuff or operating at particular volumes. We can think about how we can design for a single user or a group of users. And then, of course, you know, parts consolidation. How do we use design to explore reducing assembly and post-processing aspects? So I just leave you with my little equation, however whimsical it might be, and I thank you for your time.
Thank you. Virtual clap. So I've known Guy for a long time, and he knows I'm always delighted when he shows the chain example for removing the powder. First time I saw that, I was blown away, and ever since then also. So we have a couple of questions. I've got one in the chat, quite a technical one about slicer software for polymer printers. So I know it's okay if the answer is I don't know, but the question is, are you aware of any software that can make slices from a highly complex geometry without exporting a very large mesh or a very big file, which I know is something complicated?
No, I think there'd be more enlightened people in the room that could probably answer that question than I can.
Okay, so I'm going to say, if anyone knows the answer to that, please pop the answer in the chat.
Can I jump in on that one? Yeah, and
yes,
someone else has put it. Someone else has already put it. So Entopology are using implicit models. So one of the things when they're taking complex geometry and you've got something like a lattice within there, is you've got some of highly complicated, and if you were to export it as an STL, it would become a very big and heavy file. But they're able to import that directly onto EOS at the moment, and they're working with other people as well at being able to print directly from that. So a formulaic model rather than an STL model, which shows those benefits. So it's definitely coming along, but it's it's in development. But thank you, Guy.
Perfect.
Thank you for that.
Yeah, I thought, well, there's got to be someone in the audience who knows, and I was not disappointed.
Yeah,
Thanks to the couple of people who
the group.
commented.
Thank you.
Yep. We've got a hand up from Jonathan, if you want to go ahead and unmute and ask.
Yes, hello. Guy, thank you so much. That was really interesting. I come from a kind of slightly similar background of a traditional design background in architecture who's found their way into this technology. I think your little presentation set alongside the previous one by Martin is quite interesting. Martin was presenting all of the things that, you know, his range of technologies can do or purport to do. I think, you know, and that's, of course, that's important, but I think for any designer, it's important to understand the significant limitations that all technologies still have in order to be able to either design with them or design around them. So if you can avoid the limitations that all technologies have, a good application of proper design understanding just makes AM look better by avoiding the issues or accepting the issues and working with them. Sorry, it's not really a question, it's a statement, but you know, I think the two presentations side by side are really very, very interesting in raising that possibility.
I mean, thank you, Jonathan. I'm glad you found your way into the AM sphere. I mean, there isn't really a question in there. I mean, I kind of agree with your sentiment. You know, as I said in the start of the presentation, for me, it's about exploring what we can do with AM. You know, and changing the role really of manufacturing. You know, this is presents some real freedom. There are limitations, you're absolutely right, but it's about exploring what we can do with it and how that can impact the design process and the products that it can create. You know, that's really interesting to me.
Yeah, and I think just to add to that, I quite liked the mention, because you gave us all those great examples of all the design stuff, and then you were like, but also don't forget these other things.
Yeah, and you know, and I could have gone on for hours about the detailed design and design for additive manufacturing, but you know, I don't think that's appropriate probably for this particular audience.
Yeah. So, well, thank you very much, Guy, and to Andrew and